Hi everyone, welcome back to our channel here at The Construct, Becoming a ROS Developer. My name is Rodrigo, and today we have a presentation from one of our students, Alan. He completed the ROS2 Basics in C++ course, and at the end of that project, you can do a real robot project. So he's going to explain us what he did. Hi Alan, how are you?
Hi, Rodrigo. I'm good.
Great. So whenever you want, you can start sharing your screen and telling us a little bit more about your project.
All right, sounds good.
All right.
All right, I'm sharing it right now. Can you guys see this?
Yes, I can see it.
All right. Um, so I have the parameter bridge in the top right terminal, and I'll be running my program in the bottom right.
Mm-hmm.
So just sourcing the bash script, launching the main launch file. So basically, the first part of this program, it'll have the robot find the closest wall.
Mm-hmm.
It'll do that by rotating until the front is equal to the closest distance. Um, hopefully it's not, hopefully the front isn't, hopefully the closest distance isn't one of those pillars.
Oh, 'cause then it'll go there.
Uh, yes. I'm really certain that it won't.
So in that output, I see the front. Is that a laser scan value for the front?
Yes.
So you're definitely receiving.
Oh, that's strange. I just need to confirm that I'm using the right values of code. Give me 1 second, sorry.
Don't worry. And can you explain? You said you're using the parameter bridge. Can you explain why you're
Yes.
using that?
So originally I was using the dynamic bridge, which would connect all the topics, even the ones that I'm not using in my code.
Right, because
Um,
the robot is running under ROS1,
yeah.
right? And you want it
Um,
to use it in ROS2. Okay.
that's fairly strange.
Did you compile in source?
Yes, I did. Sorry. If I could, I'm going to adjust it slightly with the teleup program, if that's okay.
Absolutely, yeah. You can also use that joystick thing,
Oh yeah, that's true.
whatever's better.
Just to be thorough, I'll build the package again. Okay.
So does your program make it do a full rotation before it picks the smallest
Yes,
value?
yes, yeah. Um, just so that the it can scan all the points, at least for the side that I'm trying to align.
I see.
So trying to yeah, so now the front has found the closest point, and then it'll position it between 0.2 and 0.3 meters. And then once that's done, the right side will be aligned. So right now it's positioned to start following the wall.
So that
And
was the service.
yes.
And now this is the main program to follow the wall. Oh,
Oh, I think I have my values a little too fast. Sorry about that.
no, don't worry.
Oh yes.
It
I
says,
am using I'm using sim values here. So that will definitely not work.
and what was the difference?
So mostly it's just the laser scan index ranges,
Right, because it's
and yeah, it's 360 points in the sim and 720 points on the actual robot. And also the twist values are different because it seems to move a lot slower, or the I think the values are scaled, if I'm not mistaken. So I will try to use a joystick this time.
that will move it forward.
Oh,
It's a little counterintuitive. That will move it back.
ah, gotcha. Okay, third time's the charm.
All right, so it's
Some
compiled. You set
warnings
it
there.
up.
All right, so just running that one more time.
Oh, did I see it move it back a little bit?
Yeah, so it'll position the robot so it's within a certain range,
That point two,
not too
point three
close.
you talked about.
Hmm. Yeah, so it'll move backwards or forwards depending on how close it is. So that was one of the errors that
Hmm.
I think is attributed to my browser.
Oh, well, that was pretty close. All right,
Yeah,
nice. So now it's doing the main program,
yeah.
and so this project is divided then in the service part, the main program, and the action part. Um,
Hmm.
do you have an output that we can see that the at the end of this your program? Do you have something that displays what the action server did?
Yeah, so like the program stated, at the end of the action, once it finishes the action, a whole list of the points that are being tracked from when the action is called gets outputted.
Okay. All right.
Um,
All right.
yeah,
So if you want,
and
well, because it's like halfway there, if you want to just show us a little bit of your code and how you achieved
yeah,
each
sure.
section, so and while it's when it's done, we can see
Mhm.
it do its thing.
Um, I have a PowerPoint
Perfect.
that goes through that. If you want to do that instead, and then I can go to the code.
Yes.
Okay.
Whatever you want.
All right. I guess I'll just get it over
Oh, that looks pretty
here.
good. That way we can see the robot
Yeah, we
still
can.
going.
All right. So just briefly going through this little overview. I'll first go over the workspace and the package structure, and then go over the structure of each part of the entire project. So the follow wall, the find wall, and the odometry reporting. Yeah, as you can see, the feedback saying that it's traveled almost 6 meters. So
Oh, I see.
I
I
have
see.
it
Yeah.
set to a full up is 6.5 meters, give or take. Uh,
So it should be about to stop.
Yeah. Uh, yeah, so there we go.
Ah, right. Yeah, I can see.
So that's those are all the points that were tracked. And you can see the final outputted
Mm-hmm.
distance travel is close to 6.5 meters.
Nice. And that's a perfect lap.
All right, so I'll full screen this now.
Yeah, you can make this big now.
Okay. Yeah, so here's for the workspace overview. I built all my packages under the ROS2 workspace that was already created for me from the course project.
Mm-hmm.
Um, I have one custom package called Project Action Messages, which was used for my custom action interface. And then I have my other package, which is called ROS2 Project, uh, which includes all of my source code and also the custom interface for the service that I used for the find wall part.
Mm-hmm.
Brief little uh, diagram for the follow wall part. Um, so I have one node called follow wall, and it has a subscriber and a publisher. Um, and it's subscribed to the scan topic and it publishes to the command velocity topic. And that's basically how it follows the wall.
Right.
Um, so how I implemented it, create a follow wall class in the C++ program, Turtlebot 3 follow wall. And the control logic was inside of the subscriber callback for the scan topic. And I binded a timer to a timer callback function so that I can publish the messages to the command velocity topic periodically. The control logic was fairly straightforward. It mostly just followed what was outlined in the project document.
Mm-hmm.
So if the right distance to the robot was greater than 0.3 meters, it would turn left. If it was less than 0.2, turn right. If the front distance was less than 0.4 meters, I had to make a hard left. So the angular twist would be like 5 times greater than a regular turn.
Okay.
Um, and if it was between 0.2 and 0.3, then we would just have it move forward. And for the find wall part, I now have a second node called the find wall service node. And in there, the service is created. And that service is called find wall service. And back inside the follow wall node, I create the service client that calls the service and waits for the service to complete inside
Mm-hmm.
of the version program. So the way I implemented this was I created a header file for the actual code that was implemented for
Mm-hmm.
finding the wall. And in there, I created a class called findWall. And there was also a node in findWall move node, which created a subscriber to get the full laser scan values. And then inside that subscriber callback, parse through the entire list of uh, laser values and find the smallest value, which would be the closest distance. And I would ignore the infinite values.
Right, right.
Um, and then using that same node, I created a publisher for publishing those twist messages um, that would basically dictate whether to turn or go straight.
Mm-hmm.
Um, and then I had another function that was essentially a state machine, and that was binded to a timer so that it would be publishing periodically. And it would set the state of the robot depending on the laser values that it would get. So
So what states did you have?
um, basically, I can step out of this and go into the code. So there is one function for these states. So there were 5 states: stopping the robot, turning right, turning left, moving forward, moving backwards.
Oh, okay, okay, okay. I see.
Uh, and those states were set based on 3 Boolean values: front aligned, position, and right aligned. And essentially, what those mean is the front of the robot aligned with the closest value that the laser scanner picked up. And then positioned translates to, is the robot within 0.2 and 0.3 meters away from the wall. And then right aligned is the right side of the robot in line with the closest uh, laser scan.
Right.
So that state machine will, inside that state machine function, it'll publish a twist message each time the state is updated, which moves the robot. And then once all those 3 Boolean values are true, that means that the state machine is complete, and then it'll return true, which would then translate to the service finishing. And I put all of the callbacks for the subscriber and the timer into their own callback group, because I was finding that I was having a lot of blocked calls. So just to be sure, put those in a callback group. So there's another program that actually creates the service server and creates the function for handling the service, and that's in a separate program called Findable Service at C++.
And you call it from the main program.
Yeah, and then the service client is implemented in the original program that has the follow wall code. So the service client's created in there, and the function for sending the call to the service is also in there. And for the final part, which is the odometry recording function, I created a action called record Odom, short for record odometry. And there's another node that's created here called Odom action server. And in the original follow wall node, it also creates an action client, which will send the goal to the recorded DOM action server, and it will be constantly looking out for the feedback that it returns, and it also handles the result inside the action client.
Right.
So the way I implemented this, just one program for the entire action server. Create a class called DOM action server. Again, there's a node in there called DOM action server, and the action server's name is recorded DOM. In here, the goal handle functions are implemented. So there's those 3: the handle goal, the handle cancel, and the handle accepted. Basically, that just determines what would happen if it was like a bad goal, or if the user decided to terminate the action in the middle of it. And then there's an execute function that's binded to the handle accepted function, which is placed onto a separate thread because it's a long running process. And this node also creates a subscriber for the odometry topic. And it'll parse through the odometry messages, looking only at the X, Y, and Z. And it basically takes one point every second, and it adds it to a list that's tracking the points that the robot has traveled to since the action was called. And every time it adds a new point to the list, it'll calculate the distance from that point to the most recent point using the distance formula. And it'll basically just add that to a total distance variable. And that's how the action is tracking the total distance that's been traveled. And also in this execute function, it's constantly polling to see if the total distance uh, is either greater than or equal to the total lap distance that I set myself. So once it passes that threshold, then the execute function will end. The action will be completed, and then it'll send that result back. So the action client is implemented in the follow all C++ code. It basically just creates an action client using the same node and sends an empty action goal. And in here, the action goal callbacks are also implemented. So the goal response, the feedback, and the result. And these get hit at each different stage when the action is executing.
Mm-hmm.
And I'd like to mention that all the callbacks in this program were all placed into a callback group using the multi-thread executor.
Same as in the service server?
Not the same callback group.
Okay.
Yeah, they're separate. But again, I was just trying to be thorough because I was finding that a lot of my functions were being blocked by others while they were executing.
Yeah, no, I think you have to. There might be a way to do it without these callback groups, but I think you have to. So good call on that. Yeah.
Yeah. Thank you. So briefly, I want to touch on the custom interfaces that I used here. So for the find wall service, I made my own custom service interface, and that was in the ROS2 project package. So basically just create a SRV folder and copy and pasted the interface format and the variable names that were outlined in the project, and modified the CMake in the package XML. And pretty much the same thing for the action interface, except here I decided to just create my own a separate package for it, just to practice. And yeah, the interface folder called action, and same process, except the action has 3 fields instead of 2. And that pretty much wraps it up.
All right. Well, congratulations, Alan. It's a really nice presentation, really good project, really simple and straightforward. Let me ask you a couple of questions.
Yeah, sure thing.
Right. So you talked about including a header file for your functions. I think you put .cpp. I think you meant .hpp in your presentation.
Yes.
So could you explain a little bit why this is helpful and just show us how you implemented this and basically why it's useful to have a header file like this?
Yeah, sure. So I'll just pull over to my code real quick. So if I recall correctly, the purpose of using the header files is for like modularity, so that certain functions can be used in multiple implementations, or certain function definitions can be implemented in different ways in different types of programs. So this was the way that one of the action examples for the course lessons did it. Um, I
Mm-hmm.
thought it would be good practice to implement it the same way.
Right. Yeah. And so on
Um,
the header file, you have all of the functions that you will use in your package in
right.
this case, and choose between uh, public and private, so you know
Mhm.
which program can access what. And the reason why I ask is basically because you can pretty much get around without doing that, right? For a simple program
Mhm.
like this. But
Right.
once it starts getting complicated, it's a really good idea to have that header file so you can control, like you said, the modularity of it, and it's good to see that you did that. Another
Yeah.
question that I had is you talked about in your action server, you talked
Mhm.
that about executing the function on a separate thread because
Mhm.
it was a longer process. Can you elaborate a little bit more on that?
Yeah, so I know that one of the differences between services and actions is that services should be like kind of quick processes um,
Right.
that don't really require the feedback, and the calling program would be expecting a result relatively soon compared to an action, where the action was is something that's usually used for longer running processes.
Hmm.
Um, so because of that, I think, like it was mentioned in the course lessons, it was more prudent to put the function that was part of the action onto a thread because it is a longer running process, and that way you can have other things going on at the same
Exactly.
time
Yeah. Yeah. That's the
while
main thing is that you
mhm,
can have it on a separate thread and then do whatever you want in the meantime. Yes,
mhm,
exactly, because it's a longer process. The way I think about it all the time is a service is like ordering a pizza, but
mhm,
going there. So you're going to the shop, you're ordering the pizza, and then you're driving back home. As in the action way, it would be like you order it on, I don't know, Uber Eats, and then you wait for it to
mhm,
come while you do other things. So yes,
mhm.
that's good. Good way of putting it. I wanted to make sure you had that. Um, and then, I mean, other than that, um, that's all of my questions. I mean, you seem to have a pretty good grasp of everything. And just asking, what was the most difficult part of this? Would that be like the reentrant callback groups and multi-threading in that section of it? Or what, for you, what was the most challenging part?
Definitely the most challenging part was um, understanding that the callbacks in ROS2 can block each other.
Right.
Because going into this, I was not aware of that. And I had a suspicion, or and
Because
I
it
had
doesn't
like
happen in Rust 1, right? That's
mm,
for Python at least, I think. So, yeah.
um, well, I'm not very familiar with the ROS1 structure, but at least when I was implementing this project, a lot of my stuff, I was running into a lot of strange behavior where like things wouldn't update or the robot wouldn't move when things were updating.
So the perfect
Um,
example is like the scan, right? You if you
mhm,
don't do that, then the scan callback gets blocked, so you don't get new values.
yeah,
Hmm.
exactly. So there was a lot of trial and error with like creating booleans that would only execute that would skip the function if a callback hasn't been hit,
Oh, okay.
or so that was one way I basically went around that. Um, but then there was the timing issue. So if a callback, like if one callback got hit before another could get hit, then that slower one would never execute.
All right, I see.
Um, so yeah, after a lot of calling for help in the forums and reading about multi-threading, um, I learned that callback groups are the way to go with the multi-thread executor. And that's pretty much how I solved that issue. But getting to that point was uh, quite a struggle because I I had no idea.
Right. Yeah. Well, yeah. This is what this course is for. It's just to get that base knowledge under you, and
Mhm.
I mean, again,
Yeah,
Alan, this is a really nice project, and congratulations.
and thank you. Yeah, I think this course did exactly what um, it set out to do. Um, yeah.
I'm glad to hear that. I'm glad to hear that. Do you mind stopping sharing your screen so we can
Yes.
do our little outro here?
Sure
Uh,
thing.
gr- Great. So again, Alan, great, great job. It's good to see people doing our ROS2 courses. You're one of the first that have completed the ROS2, and this is good because we're as time goes on. I mean, ROS1 isn't even going to be supported after Noetic. They're not coming up with
Mhm.
new ones, so it's a good idea to start doing ROS2, and it's exciting to see that. People are doing the projects, and for everyone else that wants to learn ROS2 basics, you can do what Alan did here and show your what you learned throughout the course in a real life project that has its challenges, but it's uh, not hard enough that you get demotivated, but hard enough that you can learn all these things. So I encourage you guys to take it and do your presentation in order to get your certificate, like Alan did here. That's it for all of us, you guys. So we'll see you next time for our next presentation here at Becoming a ROS Developer. All right, guys. Thank you, Alan.
Thank you.
All right, guys. See you later. Bye bye. All right. Cool. 32